Okay, this is Math 200. We're looking at Chapter 8. So let's start with Chapter 8 notes. Let's start with the note packet from Chapter 8. And we're looking at 8.1. So they want us to solve this and this and y minus 3 quantity squared equals 4 and x squared plus 4 equals 0. All right, so let's take a look. So we did do this in the past. This isn't the first time we've solved this. We could solve that with factoring. Look up here, x squared equals 49. We could have moved the 49 over. Said x squared minus 49 equals 0. And then that's the difference of two perfect squares. So x plus 7 and x minus 7. And so then our two answers are x equals negative 7 and x equals positive 7. Two solutions. All right, so we've done that in the past already where we've factored the difference of two perfect squares. I think you can see that pretty much. Okay. Anyway, we're going to do it a different way. We're going to do it by taking the square root of both sides. But when we take the square root of both sides, we have to put a plus or minus in front of that, because there are actually two solutions. It's a second degree equation. We need two solutions. So plus or minus 7. And this is just shorthand. If you want to write it x equals 7 and x equals negative 7 like we did with factoring, that's fine. You can write it like this or like that. That's the shorthand, plus or minus 7. All right. Let's continue. What if they make it a little tougher? What if we do divide by 2? And then we have x squared is equal to 2. And then we're going to do square root of both sides. But when we do that, I'm going to toss a plus or minus on it. So we have x is equal to plus or minus the square root of 2. And then that's it. Unless they tell you to give them a decimal approximation to hundredths or something, you just leave it the square root of 2. It's in simplest radical form. That's as good as it gets. Let's take a look at this one. So it's a y minus 3 quantity squared equals 4. So we want to get rid of the squared. We'll do the square root thing and do plus or minus. And so we have this now. Y minus 3 equals plus or minus the square root of 4. Well, it's not y equals, so we want y equals, so we'll add 3 to both sides. We'll have this. Y is equal to 3 plus or minus the square root of 4. That would be fine if the square root wasn't able to be fixed. Look, this, we can't fix it. It's the square root of 2. This can be fixed. The square root of 4 is 2. That's a perfect square. So we have this, 3 plus or minus 2. Well, that actually breaks into two answers then. Y equals 3 plus 2. Y equals 5. And y equals 3 minus 2. Y equals 1. And whenever you, oh wait, it's square root, so we're good. But we could check it anyway. You can always check your answers. But if you square both sides, you must check your answers for extraneous solutions. If you take the square root of both sides, it should work. You could just check it. 5 minus 3 is 2, and then 2 squared is 4. And 1 minus 3 is negative 2, and negative 2 quantity squared is also 4. So both of those work. All right? So this, when we did back in factoring days, we wrote the word prime. That means there's no, there's not a nice solution. It doesn't mean there's no solutions. There's not a nice solution. So this one, and by nice, I mean a rational solution, fractional, like either a whole number or a fraction. If it's factorable, that's what's going on. It can be expressed as the division of two numbers. But this one is going to be extra special there are two solutions to this, and so now you're getting to see behind the curtain here, plus or minus the square root of -4. When I give you a second degree equation, that means you find me two solutions, and here's the rub, real or imaginary. And so now, after the last chapter, chapter 7, we learned about imaginary numbers. So you can tell me the two, or complex numbers, complex solutions. There's two complex solutions here. We're going to rewrite that. We're going to replace that with, for I squared, right? Whenever you have an even rooted thing with a negative in it, you replace the negative with an I squared. Still a plus or minus in front of it. And now we can evaluate that. That's perfect square, that's perfect square. So x is equal to plus or minus 2i. So there are two complex solutions to this second degree equation. All right. And that's the first page. Let's look at the next page. They've got another one that looks just like number 3. So number 5 is x plus 2 quantity squared equals 25. Number 6 is 3x minus 17 quantity squared equals 28. And then they want us to factor these perfect squares. So we're going to do a lightning round of factoring there. All right. So let's do this. We got, take the square root of both sides. We'll put the little plus or minus there. So we get this. X plus 2 is equal to plus or minus the square root of 25. We isolate the x, so subtract 2 from both sides, and we end up with this. X is equal to -2 plus or minus the square root of 25. Only the square root of 25 is a perfect square, so we can fix that. So let's fix that. -2 plus or minus 5, and then let's split it into two problems. X equals -2 plus 5, and x equals -2 minus 5. So x is equal to 3. And x is equal to -7. And both of those will work. You pop 3 in, 3 plus 2 is 5, 5 squared is 25. You pop in -7, -7 plus 2 is -5. -5 times -5, also positive 25. So two solutions. All right, this one's a little uglier. Let's see, we're gonna do the square root. We'll throw a little plus or minus on it. And so now we got this, 3x minus 17 equals plus or minus the square root of 28. We can move the 17 over, add 17 to both sides. And we can fix that a little bit, not entirely. And so we got 17 plus or minus. We can break this into perfects and leftovers. Perfect is 4, leftover is 7. And so we got this, 3x is equal to 17 plus or minus 2 square roots of 7. And now we're going to divide everything by 3. And so there are our two solutions. We've got x is equal to, you can split it up if you want it, right? 17 thirds plus or minus 2 square roots of 7 over 3, that's fine. But I'm just going to leave it like this, plus or minus 2 square roots of 7 over 3. Now, this would be a problem that if we would have multiplied that out and moved the 24 over, it would have been a second degree equation, but it would have not been factorable. It would have been prime. And the reason we would have called it prime is because it has a square root of 7 in it. And it's an irrational answer, a non-terminating, non-repeating decimal that goes on forever. And so 17 plus 2 times that number that goes on forever, and then divide the result by 3. And 17 minus 2 times that number that goes on forever, and divide the result by 3. All right, so let's look at these. These are perfect square trinomials, which means it's going to be the same thing times itself. So x, square root of 36 is 6 and 6, and now it's got to be minus minus. because that's negative 12. All right. X, the square root of 81 is 9, and that's plus, plus. And X, and that's 25, so 5, and then minus. And now what we're going to do is, well, on the bottom here, we can squeeze those in here. So if I said x squared minus 10x plus what would make it a perfect square trinomial? And if I said x squared plus 16x plus what would make it a perfect square trinomial? And if I said x squared minus 7x plus what would make it a perfect square trinomial? Well, this one was actually right above it. It would be 25. And if you think about it, you take half of this number, half of 10 is negative 5, and then negative 5 squared is 25. That's how you complete the square. It's called completing the square. So if I take half of 16, that's 8, and then 8 times itself is 64. That would make it perfectly factorable, meaning I could write x plus 8 times x plus 8. That multiplies to give me 64, but adds to give me 16. This one would be a little nasty because it would be half of 7, which is negative 3.5, and then square the result. So we'll just leave it a fraction, but that would be 49 fourths. So that wouldn't be a walk in the park. But all of those then would be factorable. This would be x minus 5 times x minus 5. This would be x plus 8 times x plus 8. And this would be x minus 7 halves times x minus 7 halves. All right. So let's look at how we do this in practice, completing the square. So if we want to complete the square, that is a way to solve a second degree equation without factoring. We've done solving second degree equations with factoring, but if it's not factorable, there are avenues we can take. You could graph it. We're not going to really focus on that until you get into the next course, college algebra. And we could complete the square. And this is going to be completing the square. Ooh, this one's going to be yucky. This one's going to be yucky. This one's not going to be bad. So look, to complete the square, what you do is you find the magic number that I add to both sides of this equation. That makes this a perfect square trinomial. So to do that, I'll pull the number. It's always the number in front of the y, or x. It's x squared plus 6x usually. They did y, so that's fine. 6, we cut it in half and square the result. So that's 3 squared, it's 9. So 9 is the magic number on this. So we add 9, we add 9. So here, we can now factor it into y plus 3 times y plus 3 equals negative 8 plus 9 is 1. All right. And now, if you take a look at this, we have y plus 3 quantity squared equals 1. We've solved that. That was on the page before. We just solved a couple of problems like that. All right, so how do we do it? We do plus or minus the square root. That square root gets rid of that. So we have y plus 3 equals plus or minus the square root of 1. And then we isolate variables, so get the 3 over to that side. And so we have y equals negative 3 plus or minus the square root of 1. Well, the square root of 1 is a perfect square. So we can write negative 3 plus or minus 1. And then we split up the band here. Two solutions. Negative 3 plus 1 and negative 3 minus 1. And so we end up with negative 2 and negative 4. Those are our two solutions. That process is called completing the square. Now, this particular one was factorable. I could have moved that 8 over to this side, and then I would have had to think what multiplies to give me 8, but adds to give me 6. That would have been 4 and 2, and then it would have been y plus 4, y plus 2 equals 0, and then the opposites. So this one was factorable. So this wasn't a really good candidate to do completing the square. This is a little better, but it's also a little worse because this has a 1. That's not going to make a really pretty magic number. So first let's move this 7 over to the other side. And because this is a 1, the magic number is going to be a fraction. Fractions. All right, so look, we're going to have 1, and we're going to divide that by 2. Always the number in front of the y. Cut it in half, square the result. So 1/2 squared is 1/4. So the magic number here is 1/4. That's not very magical. So this is factorable. We can now take that and make it y plus plus. And it's always going to actually factor into, if you looked at this one, it's always going to factor into the number before you squared it when you were finding the magic number. So look, this is going to be 1/2 and 1/2. Think about that. 1/2 times 1/2 is 1/4. 1/2 y plus 1/2 y is 1y. So it's always this number before you squared it. This is a pain in the butt because we've got to make it a 4 on the bottom. So that means multiply top and bottom by 4. So that is 28/4 plus 1/4. That's going to be y plus 1/2 quantity squared equals 29/4. So now we take it from the page before. We're going to solve that second degree equation. Let's throw the square roots on there, plus or minus on it. And so here, that squared and the square root wipe each other out, y plus 1/2. Here, plus or minus the square root of 29 I can't do anything with, but the square root of 4 is just regular 2. So the 2 isn't under the square root sign. And then we'll just move that over. And then we're done. We can't execute the square root. When you can't do the square root, it's easier. You get to stop. And so this is a little bit more typical of a problem for completing the square because it was not factorable. There's nothing that multiplies to be -7. That adds up to be 1. So this was prime. I couldn't factor it. But because it's prime doesn't mean there's not a solution. It means there's not pretty solutions. They're non-terminating, non-repeating decimal solutions. So this is the two solutions, -1/2 plus the square root of 29 over 2 and -1/2 minus the square root of 29 over 2. If you wanted to, you could go and put it all under one roof like that, since it's 2 on the bottom of both of them. It doesn't really simplify it at all, so either way is fine. All right. Let's get the next page. Oh, this one's a real nasty one. So on the test, I know we always worry about the test. There's gonna be one like this. There won't be a not factorable one, and there for sure won't be one like this. So this is a completing the square where there is a leading coefficient that you have to deal with. And the thing with completing the square is you can't have a leading coefficient. So what we have to do is divide everything in the equation by whatever the leading coefficient is before we start, which usually makes a bunch of fractions, and that makes it a messy process. So let's see here. So if I want to start this, if I complete the square of this problem, I can't have a 2 there. I need 1x squared. So the very first thing I'm going to do is divide everything by 2. So that is now x squared. That is now 7x. That is now -1/2 equals 0. All right. So let's red row over that 1/2 over. And so we got this going on. X squared plus 7x equals 1/2. And we're going to find the magic number that we're going to add to both sides that will complete this square. So what we do, we pull the number out from in front of the x. 2 things. We cut it in half, square the result. So again, with the 3.5, we'll leave it 7 halves times 7 halves is 49 fourths. So the magic number is 49 fourths, 49 fourths. So this is now factorable. I can break that into x plus 7 halves, 7 halves. Now think about that. 7 halves times 7 halves, 49 fourths. Multiplies to be that. 7 halves x plus 7 halves x. The 2 would stay the same on the bottom. 7 plus 7 is 14. 14 over 2 is 7. So it does add up to be the 7x. This, I need 4s for common denominators. That one has it. That one needs it. 51 fourths. So that's not a prime number, but it's also doesn't have a perfect in there. That's, what is that? 3 times 17. So 3 and 17 aren't, you can break it into the square root of 3 times the square root of 17, but why would you? Neither one of them is perfect, so we can't fix it. So it just stays the square root of 51. So square root both sides with a little plus or minus on there. And again, that gets rid of this. So we have x plus 7 halves on this side, no more squared. And then that plus or minus the square root of 51, I can't do anything with, but the square root of 4, I can make it into 2. And then red row over this 7 halves over. And then we're done. Again, I wouldn't do it that way. It wasn't factorable. There's what, you couldn't factor that, but I would have used quadratic formula for this one instead of completing the square. The reason that we're showing you completing the square is, again, on a problem like that, completing the square to this point comes in handy when you're graphing things. That's called vertex form. And if you go into college algebra, the next class, we're going to do that. And so they're just prepping you for that. If we were actually trying to solve this equation, I would use quadratic formula over this any day because this was kind of a pain. All right. So that is 8.1 in a nutshell. We're going to look at 8.2 on the next video.